Assalamualaikum and hi everyone. This is lesson number 2 for optical fiber communication system. This table tabulates several losses in fiber optic. The first one is scattering loss. Scattering loss is due to impurities in fiber core. Due to the impurities in fiber core, light rays will spread out in many directions. Besides that, some of the light rays will enter at the wrong incident angle and being lost in the cladding due to the refraction. Number 2 is absorption loss. Absorption loss also due to the impurities of the fiber core. Due to these impurities, lights will soak up in the fiber core. Number 3 is bending loss. Due to bending, the light rays on the outside of a sharp bend cannot travel at the same speed as the other rays. Number 5 is splicing loss. Splicing loss is due to misalignment of fiber, lack of end fiber cleanliness, and joining two fiber with different sizes. Number 5 is coupling loss. Coupling loss is mainly due to the interfaces or connectors in the fiber link. This figure shows the relationship between attenuation and wavelength. By definition, attenuation is a reduction in intensity of the light beam with respect to distance travel. Attenuation is mainly due to the scattering and absorption losses. From the figure, we can see that the lowest attenuation occurred at the third window. The wavelength is in the range of 1500 nanometer to 1600 nanometer. This window is suitable for telecommunication. This figure illustrates the losses due to bending. Due to macro bending, some of the lights at the curved section will enter the cladding and being lost. This is because it exceeds the critical angle. Micro bending loss can be happen when an external force is being applied on the fiber cable. This external force can introduce imperfections to the fiber core. Therefore, some of the lights in the core will escape to the cladding and being lost. This figure shows a splicing machine. When we open up the cover, we can see the two fibers are aligned inside the splicing machine. Electrodes will burn the glass fiber at high temperature. Therefore, the two fibers will be permanently joined. The position and the structure of the glass fiber inside the splicing machine can be viewed as well. This figure shows the splicing losses caused by fiber manufacturer and imperfect surface finish. From here, we can see that there are two mistakes made by fiber manufacturer. The first one is they have made the fiber optics with different core diameter. The second one is the core not in the center of the fiber cable. This figure shows several splicing products. The first 4 products is mainly due to the improper handling of the splicing machine. Fiber alignment impairment are caused by lateral misalignment, gap displacement, angular misalignment, and imperfect surface finish. This table tabulates several types of fiber optic connectors and their specification. These specifications is important when designing fiber optic link. In fiber optic system, a link power budget is a design allocation of all attenuation and gains in a fiber optic link. The purpose of link power budget are: number one, to ensure the receiver receive enough signal power. Number two, to ensure the receiver get enough optic signal level. And number three, to ensure the design optical system is viable. If the system is not viable, one of the following steps may be taken. Number one, use repeater or signal regenerator in the fiber link as to increase the signal power. Number two, increase the launching power by using light wave booster amplifier. Number three, changing the light detector with better sensitivity. The link power budget can be performed based on the following steps. Number one, determine the total optical power margin between transmitter and receiver. This can be done by taking the amount difference between power launch and receiver sensitivity. Number two, estimate the link loss. The losses in fiber links include cable attenuation, connector losses, source to cable interface loss, cable to light detector interface loss, splicing loss, and cable bands. Number three, check the viability of the system. Viability of the system is based on the excess power margin. Excess power margin can be calculated by subtracting total optical loss and safety margin from the total power margin obtained from step number one. Safety margin is a loss allocation for component aging, temperature fluctuation, and losses from components in the future. Typically, the amount of safety margin is in the range of 5 to 10 dB. If excess power margin is greater than 0 dB, means the system is viable. Try to understand example 3.1. Based on the given specifications, do the system link power budget and state the system viability. The link budget can be determined as follows. First, determine the system margin. The given launch power is 1 milliwatt, which is equivalent to 0 dBm. To carry 100 megabits per second data, the receiver sensitivity for indium gallium arsenide pin is equal to negative 38 dBm. To determine the receiver sensitivity, you may refer to figure 3.1. From here, the system margin is equal to 38 dB. Second step, determine the total losses along the fiber link. For 10 km fiber link, the total cable attenuation is 5 dB. Since there are 10 splicing points, the total splicing loss is equal to 2 dB. The total connection loss for two connectors is 2 dB. 8 dB is allocated for safety margin. Therefore, the total loss in the fiber link is 17 dB. The final step is to determine the excess power margin. From here, the excess power margin is 21 dB. Since the excess power margin is greater than 0 dB, so the system is viable. This figure shows the relationship between receiver sensitivities and data rate. Based on example 3.1, for 100 megabits per second of data rate, Indium gallium arsenide pin has minus 38 dBm of receiver sensitivity. Please try this exercise. The final answer is given for you. Thank you for your attention.